Okay, lecture 10, Indefinite Integral and Fundamental Theorem of Calculus. Fundamental Theorem of Calculus, that's my favorite theorem, and which is very important. And this will tell you something which you already know. Okay. Well, indefinite integral. To give you the concept of indefinite integral. Well, integral was the method, procedure to compute area. And the area is just a number. So it is definite, right? So this is self-contradictory. This is indefinite integral. So where does it come from? And why do we need this one here? If you remember the differentiation operation, the result became a derivative, which is a function. Why we needed derivative here? Because this is a function, therefore you can differentiate again. And second derivative happens to, if that is a position, then derivative is a speed, and second derivative is acceleration. So keep differentiating is possible because this is a function. So integral is once again an operation, right? So the result of operation, can we make this as a function rather than just an area value? That's the question mark here. Okay. This Riemann integral is just a value, but if you look at this T0, Tf, since you are integrating from T0 to Tf, that becomes a value, okay? But suppose you integrate from certain point to T, and if you let that T vary, then this entire thing becomes a function of T, and that could be a function. Let's do that. There are two methods, both of them are pretty much the same, whichever the one you like. The first one is easy. Whenever you don't need those values, right? So you get rid of those and don't write anything. And this becomes a function of t. Okay? So that's indefinite integral because you don't know the lower limit and upper limit. So you cannot define. Okay, or keep the lower limit at the possible lowest value, which is minus infinity, and set the upper limit as t, variable t. Then this entire thing becomes a function of t, so therefore that's f of t. Well, I personally prefer this explanation here. Okay, so both of them becomes function of t. So that's this, anti-derivative. Lack of imagination, I guess. This is derivative. If you differentiate, you have derivative. You have integrate, this is called anti-derivative. But do you know why this is called anti-derivative? Well, I guess you learned in high school that the integration is the reverse of differentiation. You must have learned that. But why that is true? Because differentiation is the operation to, compute the rate of change, right? And integration is an operation to compute the area. Those are completely different type of things. So until somewhere in the 17th century, those two were separate operations and they were not related to each other. So somebody must have found that those two are the reverse of each other. Okay? So that's the thing I'm going to talk about. But before going into that, the dummy variable is tau here. Let me let me caution you that this is not t, but tau, right? As I have said in the last lecture, you need to use the dummy variable. I'm talk a lot more about dummy variable again because this is so important. This is what the university mathematics is different from high school mathematics. Well, anyway, fundamental theorem of calculus. Fundamental theorem of calculus. This probably is one of the most important theorems in the calculus. Okay, Newton, that famous Newton who found the gravity and came up with Newton's law for the motion. And Leibniz. Newton is British. And Leibniz is German. And they independently showed that following theorem in the 17th century. So what are the theorems? What is a theorem? Let capital F of x be differentiable so that you can differentiate it, and the derivative is f of x. Then, if you integrate derivative f of x, then you get the original function plus c. Indefinite integral. If you have definite integral like this one here from a to b, then this becomes fb minus fa. Either way, indefinite integral or definite integral. And for that, f of x is given the name of primitive function or antiderivative, as I said. Primitive function here is difficult to remember, I guess, but that was a name given before this theorem, probably. I don't know. And c here is called the integration constant. Okay? So, integration and differentiations are inverse operations. Goes the other way around, right? Differentiate f of x, integrate, you got the original function. All right, so what's in here? Of course, we know this. But it was not known until 17th century. And in high school, you learn that those are reverse of each other. But it was not known. That interesting? I think this is very interesting. Okay, why the integration constant c? Well, when you differentiate it, there's no such things. You don't have to worry about that. But the integration, you have to worry about the constant. Well, usual explanation is this. d dx c constant is equal to 0. So therefore, if you set gx is equal to fx plus c, you differentiate g, then you get the same fx because differentiating c becomes 0. So if you integrate by fundamental theorem of calculus, you get g of x because of this. And that's fx plus c. That's it. Well, I guess that's fine, but my explanation is not. I said I prefer this way of writing for the indefinite integral. And what I do is I break down this one into two parts. One of them is from minus infinity to somewhere, which I call 0. Doesn't have to be, but let me call that 0. From 0 to t. And if you look at this one here, this is a definite integral, right? From minus infinity to 0. So this is a definite integral, so this is some number, which I call c. So therefore, indefinite integral becomes indefinite integral, this one here, plus c. And this is more appealing for engineers. Because engineers has to, well, we have to build something and we have to start experiment somewhere, and which I may call that 0. So you start from 0 and do something. So we record everything, data, from certain point in time on. Then what happened before that is gone. because you're not recording it. But that will have influence on what's going to happen from here to there, right? And the summary of what had happened before you start experiment is summarized in here. This is the integral. So summarized in here. So whatever the effect of what had happened before you start experiment has to be here, right? That's what integration constant is all about. Okay. Minus infinity does not exist in real world. That's another thing. Well, you cannot use this. Engineering sense, you cannot. This one, you can do it. You can start at some point. So don't you think this is much better? Coffee break. Remember use of derivative differentiation again, as I said. Okay. Then, use of antiderivative for integration again? Well, yes and no. Yes and no. But there are more things to it. Like integration twice is like this one here. You have integration here, indefinite integral. So z is a dummy variable. And after you integrate it, becomes a function of y. So you can integrate in terms of y again and becomes a function of x. So that's f of x. So this is an integration twice. But more interesting thing is that like if you have a surface here and the height and so forth, in other words, 3D space where we live, what we may end up with is a function which is a function of two variables, x and y. And you want to integrate that over a certain area or something like that. And that is called a double integration. That is another integration we use quite often. Like you find the volume instead of just an area and integrate one more direction, another direction, you get this volume. So volume computation is this integration. And of course, you can generalize that into many different, larger dimension, n-dimensional space here. You have this D domain of integration here, and you integrate this entire thing. This kind of things you can use in multi-dimensional spaces. Okay? So, antiderivatives, yes, but there are lots of applications here. Well, practical integration. So, up to here, we are talking about integration, which is the other, the reverse of differentiation and so forth. And differentiation was defined by the limit. And we asked ourselves that, do we have to compute the limit all the time? The answer was no, right? For engineers, we are engineers, so we prepare a list of derivatives, pairs, okay? And then we use rules of differentiation. And since integration is the other way around, we can use the fundamental theorem of calculus so that it's reversed, and we can use differentiation pairs backwards. By doing this, we can build a list of integrals. So let's look at the table of integration, pairs, of course, and rules of integration. Those are direct application, generalization, should I say, or reverse of what we had. All right. Caution, do not forget the integration constancy. I'm going to repeat this one again and again because that's the only difference between differentiation and integration. In the integration, you need to have this one here. Well, indefinite integral, of course. To convince you, let me do a small example. This x squared differentiated, that's 2x. But 2x integrated, that's x squared plus c. Obviously. Okay, so this is a small table There are a lot more pairs you can find in the internet, whatever you like. But x to the nth power, you have this one here. And if you look at it, 1 over n plus 1, x to the n plus 1 power. So this cannot be used for n is equal to negative 1. Because if n is negative 1, that's 1 over 0. It blows up. So you cannot do that. Then what you do here. When n is equal to negative 1, this is what you got, 1 over x, right? And the integral of that is, wow, log, natural logarithm of x. It's quite different, right? And I'm going to talk about that in a minute. But sine, cosine, tangent, that's minus cosine, sine. But integral of tangent is, whoa, once again, log comes in. Negative log of cosine theta. Ooh, wow. Well, what it amounts to is that if you differentiate this one here, you get that. Do you believe me? Well, you can try that, right? Okay. Or if you know that if you differentiate tangent theta, then you got secant squared. So therefore, if you integrate secant squared, you got tangent theta plus c. And exponential, of course, exponential, but plus c, don't forget. And some of those are typical functions. Comes up with the a cosine, n sine, and tangent, and so those inverse trigonometric functions. Okay, and those are the rules of the integration here. Linearity. You don't know how important, how useful this rule is. We use this all the time. Because we use this all the time, you forget, how important it is. Integration by parts. This is once again, if you look at the differentiation of the product, this is exactly what that written in terms of integration. Integration by substitution. You substitute y is equal to gx, then this one becomes integration of fi dy. You look, this one, you look familiar, right? That's what we have seen before. I'm gonna give you some hints and some comments on that. And these are the more practical integration, e to the 8x and sine omega, cosine omega. Well, 1 over a, 1 over omega is there, that's all. And the definite integral, this is from a to b, b to c, so this is something like this one here. You integrate from a to b and b to c. Separately, that's exactly the same as integrating through total. And a to b integration is negative, okay? Because if you integrate b to a, it goes the other way around. So delta t becomes negative of original one, so therefore minus sign here. Okay? All right. So a, b, and c, no integration constant c in the right-hand side. Did you notice that? Well, let me go back here. Here, there's no c's. Even though those are indefinite integrals, there isn't. Why is that? Simple reason. Indefinite integrals on the right-hand side. There still remains indefinite integral on the right-hand side. That's why you don't need c yet. But as soon as you evaluated those indefinite integral, don't forget to put the integration constant c. I'll give you an example later. B is differentiation of products. This one here. You remember this one here? When you differentiate this one here, you got this. And if you integrate both of them and use C, chain rule, then if G is integral of this plus integral of that, and one of them move to the other side, you get that. So this is the hint. Choose fx with easier df dx. Again, I'll show you this with the example. C is a chain rule of differentiation. y is equal to gx, then dy dg dx is equal to this one here. So, well, this is let me caution. From this one here, formally, okay, you can write d1 is equal to this one here. And that seems to be exactly what you are doing in C, rule number C. But since this involves a limit operation, this involves a limit operation, so this is not really true, but formally true. So we can use this rule informal rule, but this is very handy for us. D&E for practical use, integration intervals, we talked about. Coffee break. Why dummy variable? Well, one more time. Okay, dummy variable is so important, so that's why I'm going to talk about. But I'm going to skip this one here, dummy variable u. Fx is not good. Y, that's not good. Dummy variable varies from, okay. So this is the part which I wanted to repeat. Dummy variables varies from the lower limit to the upper limit. And as the upper limit x is a variable is varied, x in the integral dx also vary, like f2 is equal to 0 to 2f2 d2. No way, this is not right. And one more thing. Dummy variable disappears after integration operation, okay? So those three, you have to remember that. So therefore, you need to use dummy variable which is different from the original variable x. And this is something I wanted to show you here. This is a type of integral which you will encounter. And this is so important in controlling robot motion. So better get used to use dummy variable which is different from current time. Okay, that's the end of it. So next time I will go into some of those rules of integration. Well, I should say techniques of integration. Thank you.